In this first video for Math 047, I'm going to talk about the organization of numbers. We're going to determine if a number belongs to a given set. And we're going to talk about the organization of sets of numbers. So essentially for us, all numbers, any number is going to be a real number. So keep that in the back of your head. So first set of numbers I'm going to talk about are the natural numbers. Natural numbers are counting numbers. 1, 2, 3, 4. These are the natural numbers. Natural numbers don't include zero, and they are just strictly positive. There are no fractions, no decimals, just the numbers 1, 2, 3, 4, 5, nothing in between. Whole numbers, these ones here, whole numbers include the number 0, as well as the counting numbers 1, 2, 3, 4, 5. No fractions, no decimals, also no negative numbers. Now, the natural numbers, the whole numbers, they keep on going up, and they go all the way up to infinity. So, for example, with the whole numbers, let's continue with 0, 1, 2, 3, 4, dot, 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 all the way up to positive infinity. Now, why am I saying positive infinity? Well, let's just take a look at a number line. So, to make a number line, what you do is you draw a line and you put arrowheads on both ends of it. And then just roughly, approximately in the middle of this line, you put a 0. Now, anything to the right of 0 is going to be in the positive region of the number line. And all of these numbers will go up to positive infinity. Anything to the left of 0 is a negative type of number, and it's going to negative infinity. Now, whole numbers actually don't have any negatives. So if I'm drawing numbers on a number line of the whole numbers, I'm going to start at 0. So here we go. And I'm going to look at those numbers, 0, 1, and 4. So I'm going to put a dot at 0, a dot at 1, and a dot at 4. I'm not going to connect the dots to the line because what we're showing on this number line are just the number itself, nothing in between. Now, integers include both positive and negative numbers. So integers, if you're going to draw a number line, you draw a line, locate 0 on your number line, and then the integers go up to positive infinity, and then they go down to negative infinity. Now, something that's important to remember when we're talking about integers, there are no fractions in the set of integers. Now, numbers that can be expressed as a fraction, we call rational numbers. So, rational numbers are numbers that are a ratio between two numbers, like a fraction. So, all of these numbers are rational numbers. 1/2, negative 2/3, 4/1, negative 2/1. Because they are so the rational numbers include a fraction like 4/1. Well, 4/1 is, well, that's just the same as 4. Well, any number such as 4 can be written as a ratio between two numbers, such as 4 over 1, or, for example, even 8 over 2. So what you might look at and think is just, well, that's just an integer, or that's a whole number. That actually also is a rational number. It's a ratio between two numbers where the number can be expressed as a non-repeating decimal. What about decimal numbers? Well, a decimal number such as, I don't know, 4.2. 4.2 written as a decimal can actually be converted to a fraction by scaling the number up by multiplying both the top and the bottom by 10. Well, notice what I've got happening here. I've got 10 divided by 10. Anything divided by itself is 1. So I haven't really changed anything. I'm multiplying 4.2 by effectively 1. All I'm doing here is just modifying this decimal and converting it to a fraction. Well, let's see what happens here. So that's going to be the same as 4.2 times 10 is 42. Well, remember I said any number can be actually written as itself divided by 1. So that's 4.2 times 10 is 42. 1 times 10 is 10. Well, 42 over 10, that fraction, I can write that. That's the same as 21 times 2 divided by 5 times 2. Well, once again, anything divided by itself is 1. So 4.2 can actually be written as 21 over 5. So any decimal number that's non-repeating can be written as a fraction and as a rational number. Concept that people have problems with is the set notation. So in your notes, there is this code that I'm going to explain for you. So notice you've got a curly bracket on the left, and then there's an X, and then a vertical line, and then a statement X has a certain property. Well, starting with the X, which comes right after the curly line, the way you read this is all X. The vertical line you read as such that, and then you read what comes after the vertical line. So this example with set notation, it would be all X such that X has a certain property. Well, it could be the all X such that X is a member of the set of whole numbers, or all X such that X is a member of the set of rational numbers. More about this later when we actually start graphing numbers on a number line. So irrational numbers are numbers that can't be expressed as the exact ratio of two numbers. So some examples of irrational numbers are numbers such as square root of 2, square root of 3, so numbers like pi, square root of 7, square root of 11. This pi symbol is the ratio of the circumference of any circle divided by its diameter. And if you take any circle, like the distance around the circle circumference, and you divide it by its diameter, you get a number. And the number is approximate. And these two squiggly lines mean approximately 3.14. Well, it turns out that pi has been calculated to billions and billions of decimal places. And the number never repeats itself. Like you always get a non-repeating sequence of digits as you keep calculating out the numbers. There's a fellow at SFU who's calculated pi to several billion decimal places. Last I heard, still working on more. Now, because the number pi has a non-repeating decimal, we say it's a irrational number because you can't actually express it as the exact ratio of two numbers. Same with something like the square root of 2 or the square root of 5, square root of 7, 2, 3, 5, 7, 11. These are numbers that don't appear in any times table because you can't take any two numbers other than 1 and the number itself and multiply them together to get 7, for example. Like nothing on the times table multiplies together to make 7. 2 times 3 is 6. 2 times 4 is 8. But nothing multiplies together to make 7. 7 is called a prime number. Same with 11 or 3 or 2. Anytime you take the square root of one of these prime numbers, it's going to be an irrational number. And that's just something you have to sort of memorize. It turns out that all numbers are real numbers, and real numbers include natural numbers, whole numbers, integers, the rational numbers, and also the irrational numbers. Now, there's a graphic in your textbook that deals with this. So, the way that you categorize numbers, if you want to sort them, the natural numbers are on the inner box. The natural numbers are contained in the box of the whole numbers. The whole numbers are contained in the integers, and the integers are contained, well, in the rational numbers. However, the irrational numbers are their own set, and they're not directly related to any of those other sets. The thing is that when we consider the natural numbers, whole numbers, and rational numbers, as well as the irrational numbers, the collection of all these numbers are real numbers. And what you need to be able to do is you need to be able to sort numbers and determine what sets they belong to. So I've got my first example, identifying elements of a set of numbers. Well, I've written the elements of the sets that I'm going to try to categorize at the top here, and I've made a and then what I've done is I've gone across the page. I've indicated the natural numbers, the whole numbers, the integers, rational numbers, and real numbers. Here I've identified the different symbols. R is for real numbers, Q for rational, I for integers, W for whole, N for natural. So let's get started. All right, negative 5.3. Negative 5.3. Well, because it's got a negative sign, it cannot be a natural number because no natural numbers are negative. It can't be a whole number because no whole numbers are negative. It can't be an integer because it's got this decimal bit. So because it's a decimal, it's 5.3. 5.3, negative 5.3 could be written as negative 5.30 or negative 5.300 or negative 5.3000. They're all the same number, and they have an exact. They're an exact number. They don't have a non-repeating decimal. Sorry, they do have a non-repeating decimal. So the last digit would be negative 5, like this. It doesn't matter how many zeros I put there, it's the same number. So that's a rational number. So that's where I'm going to start. Negative 5, rational number, a real number. A negative 5, once again, is not natural or a whole because you can't have any negatives with either the natural or the whole numbers. But it is an integer. And being an integer, irrational number and a real number. Negative root 3. Well, negative root 3, remember the square root of a prime number is irrational. So it's not natural. It's not irrational. It's irrational. So all it is a real number. Negative 1, there are no negatives with the natural numbers, no negatives with the whole numbers. It is an integer. And it's also a rational number and a real number. Negative 1/9. Well, it's a ratio, it's a fraction. Doesn't matter the negative sign because you can have negative rational numbers. So negative 1/9 is a rational number and a real number. 0. Well, 0, natural numbers don't contain the number 0, but the whole numbers do. So 0 is a whole number. And because 0 is a whole number, that means it's contained in all the other sets. They're all contained one within the other. But 0 is an integer. We've seen that on a number line. And it's also a rational number because you could say, well, 0 is the same as 0 divided by 1. So 0 actually is a rational number. It's a real number. 1.2. Well, it's a decimal. The decimal number is rational. It's a rational number and a real number. 3/2, it's a fraction. It's a rational number and a real number. The number 3, well, this is the first number that we've come to that's actually a natural number. And it's also a number and an integer and a rational number and a real number. Square root of 11, square root of a prime number, it's irrational. So the only thing it is a real number.